Okay, well, good morning, everyone. My presentation is going to be of a slightly different tone than most of the presentation you have seen before. Mathematics of environment. The environment I'm going to speak about is the sun. Mathematics, well, what I'm going to speak about is an application, a standard application of assimilation to a specific physical problem. So in that sense, I won't do new mathematics or anything very original from the point of view of the underlying theory. Okay, this shows the variations of solar irradiance over a number of years from 1975 to 2005. The solar irradiance varies with a period of about 11 years. Over one cycle, it varies by approximately 1 watt per square meter. That is less than 1,000th of the total irradiance. And together with irradiance, other quantities, other observables also vary in phase, in particular the number of solar spots, which is maximum when the sun is most active and minimum when it is less active. The period is approximately 11 years, but there are fluctuations in both the length and the amplitude of the oscillation, in particular on the last cycle that you see here. And actually, it is known that the cycle is associated with a reversal of the direction of the magnetic fields, which reverses every 11 years, so that the real cycle is 22 years. So,
it's worth mentioning that there's most variability, there's most insolation when there are the most sunspots.
Yes, yes, absolutely, absolutely.
You might think
absolutely, you might think otherwise. You might think that because there are sunspots, less light is emitted, but that's not the case. So I'm going to say a few very basic facts about solar magnetism, describe briefly the numerical model that we've been using for our work, describe the available observations and the assimilation experiments which we have made, both twin experiments and assimilation of real observation. And I'll end with a prediction for the next cycle and a few conclusions. But again, a presentation of a cycle. On the top, we have the so-called butterfly diagram for a number of cycles starting in 1870. So each cycle starts, for instance, look at the one at 1880. This is the position, the latitude time position of the solar spots in time. So each cycle, look at the one at 1880. The spots appear at about latitude 30 degrees, both in the north and the south. And then they move, not the individual spots, but the position of the spots move toward the equator, and at the end of the cycle, they are very close to the equator. And then a new cycle starts with spots at latitude 30. So the whole thing is modulated in time. And this doesn't go to, this is not up to date, because right now we are at the end of cycle 24. The cycles are numbered, cycle 1 being in the middle of the 18th century. We are at the end of cycle 24 and waiting for the start of cycle 25. And the number also of sunspots varies, and it is represented by a normalized number called the Vous number. And you see that the number of spots vary very much. In cycle 19, there were many spots, and in cycle 24, the one which is finishing now, the number of spots has been rather small. And you know there was a long period in the 17th century where apparently no spot was at all for several tens of years. So-called Maunder minimum. Okay, all that is interpreted as occurring in the convective zone of the sun, which is the outer third of the solar radius, a region where very strong convection is occurring, and in particular a region in which the differential location is marked as the various latitudes. The rotation of various latitudes is variable, while the inner core has constant rotation. Of course, this is due to the circulation induced by the convection and the associated Coriolis effect. The structure of the convective zone is not very well known. From heliosismology, we have some knowledge about it, and basically there are cells which have some similarity with the Hadley cell of planetary circulations, but there is evidence that at some period there is one cell in either hemisphere, but other period there are several cells in the radial direction and also in latitudinal direction. But all that is poorly done. This is just a schematic view. This is not built as a result for observations. So, yes? Actually,
is there evidence that this picture is true? Or
yes?
Is there evidence that the previous picture is true, or is it just...
Oh, there is evidence that there are periods in which there are several cells in the radial direction and also in the latitudinal direction. But the evidence, from what I know, the evidence is rather, the observations don't bring much information about what actually occurs. But yes, there is evidence that there are different structure of cells at various time. So, prediction of a solar cycle. Of course, it has some interest in itself. But actually, there is something else. Solar flares and associated geomagnetic storms can create very significant damage on the surface of the Earth. In 1859, there was such a storm called the Carrington event, which caused a major havoc in the telegraph system of the people. Actually, there were a number of casualties. And it is estimated that if an event like that hit the Earth in the United States, the cost would be several $1 trillion. And there might be casualties. One such event missed the Earth a few years ago by 9 days on the orbit. And of course, there will be similar events. So there is no hope at this time to, well, such storms, flares are observed. So there is time to give an alarm, and for instance, to ground the planes, ground airplanes. But there is no prediction of flares. But what can be predicted at the present is probability of occurrence of flares. So, what's the physics behind it? Well, it's magnetohydrodynamics. On the top, you have the so-called induction equation. B is the magnetic field. d divided dt equals these two terms. The first one expresses v is the velocity. V is the velocity vector. The first term expresses that the magnetic lines follow the motion, just as vorticity lines follow the motion in barotropic inviscid motions. The second term is the diffusivity. And if you want to completely simulate that, you have to use magnetohydrodynamics. So add the equation for momentum with the Lorentz force, J cross B, where J is the current density, which is actually the curl of the magnetic field. And all that creates a linked evolution of the magnetic field and the velocity. Well, in what we've done, it's simpler. We've used what is called the Babcock-Leighton model, flux transport field model. It is based on approximation. Velocity is given. Actually, I must say that I've not fully understood the significance of the underlying approximations and also the consequences of the simulation. Don't ask me questions about the theory or the reason behind the model. And velocity field is given, and so the model uses only the induction equation, dB over dt. There is an assumption of axis symmetry, and so the magnetic field is represented by two components of the magnetic field. Well, when speaking of magnetism, there is the toroidal component. This is what we call the zonal component when we speak of velocity field. And there is the poloidal component. This is what we call the meridional component. So the variables we have is b phi. Phi is the longitude, which is the toroidal component, and the scalar potential a phi, of which the boloidal component results. There is, of course, a condition of non-divergence of magnetic field. With the equation of the Babcock-Leighton models, I say frankly that I don't fully understand all the terms in the question. But yes, this work has been done with colleagues from several institutions, Sacha Brun, Alexandre Fournier, and others, and these are the people who know best the physics behind the equations. Anyway, the model, if B with constant velocity V given, and realistic value for the physical parameters, this model produces a realistic 22-year cycle with reversal of the poloidal component every 11 years. So basically, it contains the physics of the cycle. If you put fluctuations on the velocity V,
Sorry, when you say realistic parameter values, I mean, you know, the diffusivities.
okay, you mean
the magnetic, it's off by orders of magnitude.
are not perfectly known. This is what you mean. Okay.
No. It is known that the ones that you need to use in simple models, you know, are orders of magnitude off the ones that really produce magnetic field.
Yeah,
the same in the sun as in the earth.
If you put fluctuations on the velocity field, or for instance on the initial magnetic field, then you get fluctuations in the period and amplitude of the cycle. So what we're interested in is controlling the cycle, determining what controls the fluctuations in the amplitude and length of the cycle. So what observations are available? In this context, I spoke about heliosismology, which gives some notion of the structure of the motion in the convective zone, but we don't use them. There are two observations, sunspots. It's monitored and very regularly observed. So on the left, you have the oscillation of a sunspot for cycle 21, 22, 23, 24, the one which is just finishing, and the number of sunspots in this last cycle has been much less than in the previous ones. And the second observation is line of sight. The model does not produce sunspots. So how shall we assimilate observation of sunspots? Well, the proxy is defined, a pseudo-Wolf number defined as the integral of a square of the toroidal component of the magnetic field in the depth of what is called the Tacoc line. The Tacoc line is the lower boundary of the convective zone. And it is considered that it is where the process which create at the surface the solar spot are active. So solar spots are represented in the model by this pseudo Wolf number. And of course, it can be separated into a component for north and component also south. Yes, the tachocline is at position 0.7 solar radius from the center of the sun. So the integral from 0.7 to 0.71. And then the second type of observations are observation of the line of sight, what to say, of the magnetic field at the surface of the sun. And here on the left, you have observed values. Here is someone which have been smoothed out. And the pattern is similar to the butterfly pattern I showed you about the solar spots. So we did variational assimilation of that, minimizing an objective function of a standard form, deviation between the observed values of the line of sight magnetic field and the model value, plus deviation of a number of sunspots as observed and as simulated by the model. So in the first set, we do twin experiments, not identical. The velocity field is defined as the superposition of two patterns, one symmetric and one anti-symmetric with respect to the equator. The coefficients of the velocity field as the coefficients which multiply these two patterns. And the control parameters are the initial magnetic field, 20 toroidal component and 20 poloidal potential, plus two parameters defining the velocity field. So the assimilation have been performed over 40 successive one-year windows. Well, this shows that the coefficient of the velocity field has reconstructed to a satisfactory degree of accuracy. This shows the poloidal and the toroidal, the two components of the magnetic field. I will not comment all that in detail. You have results from year 1 on the top row and for year 10 in the bottom row. And if you look carefully, you'll see that the accuracy, this is the difference here between the real reference field and the reconstructed one. And you'll see that after 10 years, the difference is smaller than after 1 year. So accumulation, cycling the successive assimilation. Each assimilation is simply started from the result of the previous one. Incidentally, implementing variational assimilation in this nonlinear system turned out, and was frankly much more difficult than what I thought. When I experienced with the atmosphere, I thought it was just what we are realizing. It was not. It wasn't. It was difficult to implement. These are results again for, well, simulations over 40 years. The blue curve corresponds to an integration of a model in which no observation was introduced. You see that you gain significantly by doing the assimilation. The vertical scale is logarithmic. You have the toroidal component at the top and the poloidal potential on the bottom. And in the forecast phase, you see that there is a predictability time of a little more than 10 years. It is more than one cycle. Okay, that's for sunspots. Same thing. I'm not going to comment on that in detail. Just, if you look at the forecast phase, the top panel is for the northern hemisphere. You have the free run, the one in which no observations have been introduced. You have the analysis, the green, in the forecast phase, the forecast, which is the green curve. And you have the reference trajectory, which is the truth. And you see that the forecast and the reference are in phase until year 60. Then the phase is lost, and the amplitude is relatively correct. For instance, the 2 cycles in the forecast phase, the amplitude is correctly simulated. In the southern hemisphere, there is much less predictability, as you can see. 5 minutes, okay. So, I don't know. Okay, now real thing, real observations. I've described the observation a few minutes ago. So these are assimilation performed. Now, the assimilation period is 1 cycle. So these are assimilation for cycle 21, 22, and 23, with forecast for the next cycle. So, sorry. In the first 2 columns, you have the results, the prediction for the time of occurrence of the maximum of a cycle, 90, and the number of sunspots. You have various results depending on the parameter x, which I don't describe. So these are forecasts for cycle 21. For cycle 22, through assimilation of assimilation over 21. And so forecast for assimilation for cycle 23, and forecast for cycle 24, the last one of all. Okay, so for instance, you see that, and the observation on the last row, and you see that, for instance, the time of occurrence, N21, maximum observed, 1990, 2001, 2013. There was 10 years, 10 and a half years, and more than 12 years there. And this is reflected in the observation. So the different length of a cycle has been predicted. The fact that the cycle, the maximum between cycle 23 and cycle 24, the length of time was much larger than the previous cycles, has been predicted if you look at the values that were predicted. And if you see the number of sunspots, you also see, for example, in cycle 24, the number of sunspots I've showed you was much smaller than before, and this is present in the prediction. So there is predictability, not very accurate predictability, but there is predictability. And now, these are the results for cycle 25. We are now in the between cycle 24 and cycle 25, and a quiet period, actually a very quiet period compared with previous such period. And this is the prediction for the next cycle. Maximum intensity in 2020, the beginning of 2024, and number of sunspots below 100. This has been done in response to a call by the NASA and NOAA, which called everyone who wanted to submit their forecast to submit it, and a number of forecasts have been submitted and compared. Almost all of them predict, like in this experiment, a weak cycle. So we'll see what happens. Of course, among the predicted, among the various methods, some are simply used correlations between successive cycles, because as you've seen, there is a correlation between the various cycles. So that's just statistical correlation is a way of prediction. And so we'll know in a few years which were the best of this forecast. And where similar work has been done by other people with another Babcock-Layton model, in particular, Dick Patty and colleagues did twin assimilation with an Ian Greif, 182 members, and the result they obtained in terms of quality is very similar to ours. I mean, there's no significant difference between their results and ours. Conclusions. Assimilation of observation of the solar cycle is still at a rather early stage compared to what's done now, even operationally in the atmosphere evolution. All that is a very early stage. But it produces results which show that useful information can be extracted from the available observation and that there is a predictability at least over one cycle. Next stage, well, further study of predictability, structure of the unstable modes in the model. We know that the dominant point of exponent corresponds to about one cycle period, about 11 years. And improvement of the model, of course, inclusion of a Lorentz force, so that a coupled magnetic field velocity evolution. Okay, well, that's all. Thank you.
Thank you, Olivier. We have time for a few questions.
Speak up, please, Lav.
Yeah, I'm going to take the microphone. You mentioned there is a Maunder minimum.
Mentioned there is?
You know, you mentioned there is a time period in the past where people...
Yes, there was a period in the past, the so-called Maunder minimum.
Exactly. And so are you able to reproduce this?
No, we have not tried to say. Actually, no. Our model... We could, of course, fiddle with the parameters and see if we can, but our model does not produce long period. It does not produce. It produces cycles with various amplitudes, but it doesn't produce long period without Mach cycles.
Okay.
Still, no. Of course, as you know, this Maunder minimum is considered as one major cause, if not the cause, for the cold period that occurred, the Little Ice Age.
Since I've also dabbled a little bit in matters geo and heliomagnetic,
yes.
First of all, congratulations. You know, it's a new area of applications. I wanted to, first of all, it's a Lorentz force with a T.
Oh, good, absolutely right. Absolutely right. Of course.
The other one is that, again, following up on the previous comment about the presence of sunspots being indicative of higher luminosity, you know, there has been a connection made by Korchers between the Maunder minimum and the reign of the Sun King, Louis XIV, except they were wrong, because actually it was less luminous during the Maunder minimum.
Yes, absolutely.
And I also wanted to comment on the analogy between the Maunder minimum, which was discussed just before, and the period of low ENSO activity in the late 20th century. So times like that are particularly difficult for models that, you know, essentially rely on the oscillations to reproduce. And again, you know, I think that given the level of accuracy of these dynamical forecasts, which again with parameters which are way off realistic, maybe, you know, reservoir neural networks can be quite competitive. Since I see Brian here, I was wondering, you know, looking at numbers now. You know, I just want to say that for ENSO, our, you know, data-driven forecast is still quite competitive in as far as the SOI itself is concerned. Of course, not all the detailed phenomena outside. Anyhow, so again, keep up the good work.
We should continue on from here. Let's thank Olivier once again.